So, group theory, my first lecture on this topic. So, we will begin with an introduction. Uh, Basically, we'll start by saying we'll give a formal introduction to groups, then we'll go to the abstract definitions. So, first, when you study group theory, uh, the first question arises: why groups? Why do you study this topic? Uh, so, what are they basically? What are these groups? I mean, groups are symmetries. Groups are symmetries, and what are symmetries? So you all know what is a symmetry. You can consider the reflection as a symmetry. By I am giving an example. Say consider the square. We can just take this axis and reflect it along this axis, and this is the symmetry of the square. So symmetries are very important and often found in nature. Like we have in trees, we see symmetries. In human body, we find symmetries. There's no many examples of symmetries in nature. How do they behave? And that's what exactly the study of group is. So one is this reflection, and also you can consider this axis as as reflection. So what are other ways of looking at this? Basically orientations to load angles to look at an object, and you can consider this as an on it, and this rotated it remains the same. So it's a different ways of angle rotation to angle to look at an object. It's basically consider it is a rigid motion, but we don't change the place of this object, and that doesn't matter. We're just taking this, rotating it, can rotate it. Yeah, I'm going to that. We can rotate this also, or we are reflecting it along an axis and we're keeping back it in the same place. And how many ways you're getting? Suppose all of these corners are different, name different, or you can consider the edges as well. So how many ways you're getting? So see, for example, of square, as we say that rotation is a symmetry. One rotation is so this we name it different. We can rotate this by 90 degrees, and that square remains the same and put in the same position. So this becomes a this comes here, this comes here, this comes here, and this comes here. This is rotation by 90 degrees. Also, we can rotate. Now we can rotate this by even more 90 degrees. Basically, that amounts to rotation by 180 degrees. And finally, you can rotate by 270 degree, and then it goes back to the same place. Go to 180 degree and 270, then it comes back to the same place. The rotation by 360 degree amounts to the same thing. And then you consider reflection. You can reflect it along this axis. You can reflect it along this axis. You can reflect it along this and the two diagonals. So total 8 uh, symmetries of a square we are getting. And suppose it is considered this star. You can take symmetry of any random object also. So you can consider this star and see this. How is the star behaving? What is the symmetry of the star? So each of them is different. So each of them is oriented. They have a different orientation. That basically means that each of them are different. That's not the same. This is different. This two are different. This every vertex is different. So that's different. Every vertex is named in some way. So one symmetry is we can rotate it like this. Take back. So like this comes here. This comes here. This everything shifts. And again we can rotate it by this. Again you can rotate like this way, one more rotation, and this comes here. So we can rotate it five means we can just rotate here. This comes here, then this will go here, then this will go here. So basically, there are five rotations you consider. So one is a rotation. So what is this? So basically, rotation by uh, along this, then rotation, then again rotation. So there are five rotations, and these are the only symmetries of object of this object. So you can't reflect. So well, so basically also you can reflect this also. So you understand what a symmetry is. Uh, Symmetry is so even if you reflect it along this, but this is not a symmetry because we just have same. So we are considered to say what is a symmetry because you guys know I guess what a symmetry is. It should remain the same along this axis. It should remain identical even if we rotate this or move this. So it's basically the identical. It's the same thing, different ways. We're looking at it. We're changing our rotation, looking in different ways. So consider this one. So we just given some points. There are some arrows, some points on this. So we consider the symmetry of a line with some points on there. So what is the symmetry of a line? You can't move. You have to keep it as it is. Only way we can do is that we can shift these points by one place, or we can shift this point by two places, or three places. Or we can also shift it backward by one place, or shift it backward by two places. Like this, you can continue. So that is basically that amounts to Z symmetries. That's totally Z means that integers. Set of integers is the set of symmetries of this. So if set of symmetries, the shifting is the symmetry. The shift, how many units we are shifting. Now let's come to something like now we can see one thing. One time you rotate this. Suppose we're coming to this a square. It's example of a square. Get back to the example of a square. So A, B, C. If we reflect, suppose we reflect it by 180, then we reflect it by 180. It gives a reflection of 270 degree, which is again a symmetry on its own. I mean rotation, not reflection. Uh, Similarly, if we rotate it by 180 degree, then we rotate it by 180 degree, it gives to the 360 degree. It's a 0 degree rotation. Actually, considering that is one. 0 degree rotation is also symmetry. We keep it as it is. That's a symmetry. You can reflect this once and then reflect it back again. Then it's again we get the same thing. It's a symmetry. It's again a symmetry. So basically we do two symmetries. That's again a symmetry. If we do one symmetry composed by the other, that's again a symmetry. So also you see that this is we consider the 0 degree rotation. That means that is the same as it is. We can compose it. Composition basically we can just do it after any symmetry. It remains the same. We're considering the set. We are dealing. So basically, you see, we're dealing with a set of symmetries here. Then we can also do something like we go back 90 degree, 180 degree. It goes back here again. How many? We can 90 degree. We have to get back to its original place. So we have to rotate it by 270 degree. Similarly, we have if we rotate it by 180, we have to rotate it by 180 to get back to its same again to its original place. So, but the order in which you do it matters actually. If it rotation, rotates of rotation doesn't matter. 90 degree it goes by 180 degree. It doesn't matter if we rotate it by 180 degree and rotate it by 90 degree then. But if we do a rotation you'll see you can check that if we do a rotation followed by reflection, a reflection followed by rotation, they both give different symmetries of the object. So this is a basic idea of group. So now we'll coming to the this is a group. So basically you will see these groups are following this basically same properties. The groups and the first abstract notion of the group I am coming to it, and that was given by Arthur Cayley. Arthur Kelly. There are many people who did work on this, and Lagrange and so many other people who did work on this. So, what are the properties of a group? First, we have a group, a set with a binary operation. A binary operation is a binary operation of a function. It's a map from G cross G to G, such that function from G cross G to G. So, if any two elements compose, any two elements operated give into the same set. The element, the image of that under that operation is in the same set. So next thing comes is this associativity. And you can see that the symmetries are also associative. This is equal to this a star b star b. I apologize for my handwriting. Uh, star b star b. So this allow G with the set to its associativity and binary operation is called a semigroup. Okay, it's a semigroup. So and one more thing, uh, there exists an element E. In that case, it was a 0 degree rotation. There exists an element E in G called the identity of G, such that it should be both sides. Okay, that A star E is equal to A equal to E star A. Now for each A, now this is this unique. Okay, this thing is unique. E is unique for each, unique for every group. For then we were something which is unique for every element. For each A belongs to G, there is an element of G called the inverse of A. That A star B is equal to E. B star A. This B is denoted by A inverse. And now, what is now this is the formal definition of a group, and this is exactly, not exactly, but well, this was the notion given by Arthur Kelly, who also invented the symmetry groups. We're coming to it later. So you see that the set of symmetries of a square follow this property. Okay, let's come to the other definition. What are ways it satisfies this property? Z with plus, additive under addition, Q under addition, R under addition, all satisfies this property that you can check. In Z, the identity is 0, and also there's a minus A. And one more thing is that natural numbers under addition is not a group. The identity is 0, which is not natural. Also, if you include 0 in it, still not a group. It's a monoid. Yeah, I forgot this to say. If it doesn't have inverse, the inverse condition is moved, then it's called a monoid. It's a monoid, but it's not a group because the inverse is not there. The set dot is not a group. It is not a group because the inverse is not there. Q dot is not a group, but well, even though Q dot is not a group, we can remove 0. It's a usual multiplication. We're considering usual multiplication, usual addition. You can define it in different way, and in a different operation, different way. We found that this is not a, this is a group, and for that this is a group. So this is the group. This complex plane, complex numbers is a group. So well, this is what you have to get. This is the abstract notion of the group. So if you look for more examples of groups, there are more examples. More such examples you'll find. Well, I will come back with more examples in the next video. And this is a short video, and this is kind of a introduction to the group and the abstract idea of a group, what a group is. You can think of more examples of a group and check the set of symmetries as a group, and check all the symmetries of group. And also there's one more thing, you can check that a triangle, the set of symmetries of a triangle, it's a group. You can check the symmetries of a circle. It's a very interesting thing. And also check the symmetries of this letters like B, C, D. You can check this. These are all forms of group, and that was what uh, groups was actually meant to find. That was the symmetries, to measure symmetries. As said, as a famous guy once said that the groups measure symmetries. And also the reason why the people started thinking about groups was polynomial equations. The famous people who worked on these groups and all, they first sought to find polynomial equations, to find the roots of a polynomial equations, and that is why they invented groups. So well, uh, this is how they came. There are many people like one of them was Galois, and so many other people who contributed to this group. There was Felix Klein and all. So well, I'll coming to next, and this is all for this video. Thanks a lot. Okay, so this is how I end it.